Hello and welcome to my channel. Have you ever asked ChatGPT or another AI model the same question twice and got two completely different answers? You are not alone. Large language models or LLMs don't always repeat themselves, and that is not a bug. It is actually how they are designed. In this video, we will explore why and how LLMs respond differently to the same query. I will discuss not only why LLMs behave this way, but also how you can control their consistency when it is required. At the end of this video, I will also provide a Python code example to explain this behavior. So please watch this video till the end. Let's get started. A process is called deterministic if given the same input and context, it always produces the exact same output. A process is called non-deterministic if the same input and context can sometimes produce different outputs. LLM is non-deterministic. LLMs are designed to be non-deterministic so that they don't just repeat the same rigid answer every time. This randomness makes them better at creative tasks, exploring alternatives, and avoiding repetitive outputs. Have you ever asked your friend the same question twice and received two slightly different answers? Maybe you asked, "What should we eat for lunch today?" And the first time they said pizza, but the second time they replied, "Let's go for noodles." They didn't change the answer because they were confused. It's because people consider multiple valid options and respond based on mood, context, and memory. Surprisingly, large language models such as ChatGPT behave in the similar way. If you ask an LLM the same query multiple times, you might notice that it doesn't always give identical answers. This can be frustrating, but behind this inconsistency lies an interesting mix of probability, randomness, context windows, and model design. Note that even if we have same language model, same context, and same input, different outputs may be generated by LLM. Therefore, we are going to discuss the how part, the reason behind non-deterministic nature of LLMs. Before I proceed further, we need to understand two important concepts called logits and temperature related to LLM. When LLM processes your input and predicts the next token, for example, word, subword, or character, it doesn't directly output probabilities. Instead, it outputs raw scores called logits. The logits are assigned to each possible next token before applying any probability transformation. Logits are nothing but vector of numbers. After processing the input prompt, the LLM outputs a vector of numbers. Each entry in this vector corresponds to one token in the token set. For example, if the token set has 50,000 tokens, the model outputs 50,000 logits. Think of logits as the unpolished confidence signals the model has for each possible next token. Temperature is a parameter used to scale logits before converting them to probabilities. It controls how confident or random the model behaves. Low temperature makes the model stick to the most likely answer. Therefore, in this case, model is more confident and repetitive. However, high temperature encourages diversity and creativity in the response. Let's talk more about temperature, a key parameter that controls how creative or conservative the LLM's responses are. Mathematically, if the model produces logits Z, we rescale them by dividing with numbers t. So, Z prime is equal to Z by t before applying softmax. When t is less than 1, the distribution becomes sharper. The model strongly prefers the most likely token. Think of it as confident and conservative. When t is equal to 1, the distribution is unchanged, a balance of diversity and accuracy. When t is greater than 1, the distribution flattens. The model becomes more exploratory, even picking less likely tokens. And in many libraries, t is equal to 0 means greedy decoding, where the model always picks the single most likely next word. So temperature is like the creativity dial for AI responses. More temperature leads to more creativity and thus more diverse responses. However, note that temperature doesn't create randomness by itself. It enables or suppresses it. If you sample from the distribution, higher T increases variation. If you don't sample, output is deterministic regardless of temperature. Let's understand the effect of temperature with this chart. At low temperature, T is equal to zero point 0.5, notice how the distribution sharpens. The highest probability token dominates. The model becomes very confident but also repetitive because it sticks to the most likely choices. At medium temperature, T is equal to 1, the distribution looks neutral. This is the baseline where probabilities directly reflect the raw logits. It's a balanced mode. At higher temperature, T is equal to 2.0 or more, the distribution flattens. Less likely tokens gain more probability, meaning the model explores more options. This increases creativity but also raises the risk of incoherent or off topic responses. So, temperature directly controls the balance between accuracy and diversity in model outputs. Here is what happens each time the model generates the next word. First, the model produces logits, the raw scores over the entire token set. We may rescale them with temperature to control sharpness or diversity. Then we apply softmax to turn those scores into probabilities. Optionally, we narrow down the output set with top K selection, keeping only the most promising words. From that probability distribution, we draw one token using a random number generator. That token is added back into the context and the whole process repeats for the next word. The key thing is step 1 to 4 decide if the output is deterministic or variable. This is where randomness, creativity, or strictness gets injected into the model's behavior. Here is how token selection in language models really works. Think of probabilities like a roulette wheel. In this case, cat takes up 60% of the wheel, dog takes 25%, and house takes the remaining 15%. Now, the model spins the wheel using a random number generator between 0 and 1. For example, if the random number is 0.47, it lands in the cat section. So the model chooses cat. If the random number is 0.73, the pointer falls in the dog range and the model chooses dog. If the random number is 0.95, it lands in the smaller slice for house. In short, the model doesn't always pick the highest probability token. It samples from the probability distribution using randomness. That is why you might get different responses even with the same prompt. So, in the real world, you can think of an LLM as a storyteller. If 10 people ask the storyteller the same question, you might get 10 slightly different stories, all rooted in the truth but flavored with creativity, probability, and memory. Now, let's have a look at the Python code. Using Python code, let us look at how token sampling works with temperature. We start with three tokens, cat, dog, and house. Each token has a model score called a logit. These are not probabilities yet, they are raw numbers 2.0 for cat, 1.0 for dog, and zero point 0.5 for house. To turn logits into probabilities, we use softmax function. It exponentiates the scores, normalizes them, and gives us values that add up to 1. That way, each token gets a probability based on its relative score. Now comes the key step, temperature scaling. We divide the logits by a temperature value T. If T is less than 1, the distribution sharpens, so the most likely token becomes even more dominant. If T is greater than 1, the distribution smooths, so the less likely tokens get more chance. After scaling, we compute probabilities, then build a cumulative sum. Think of it like a roulette wheel where each slice corresponds to a token. Finally, we test with random numbers 0.47, 0.73, and 0.95. For each random number, we check which slice it falls into and pick the corresponding token. At t equal to 0.5, the probability is sharpened, cat dominates, random number generator is more likely to pick it. At t is equal to 1, we see the balanced or original distribution. Balanced distribution is close to original logits. At t is equal to 2, the distribution flattens. Dog becomes more likely even though it had the medium logit. This shows how temperature changes the roulette wheel slices before sampling. If you are interested in exploring more about machine learning, data science, and large language models, please use the links in the description of this video for exploring more questions and answers like this. Thanks for watching. I hope you enjoyed this tutorial and found it insightful. If you learned something new, please like the video, share it, and subscribe to the channel. Also, consider sharing your thoughts in the comment section. Please don't forget to subscribe for more interesting tutorials and the latest updates. For more questions and responses like this, please follow the links in the description of this video.